Good morning, everybody. Last time we looked at stochastic processes in general, and in particular, I took the example of a random walker on a periodic lattice to develop the theory and to show how to do an expansion in the eigenmodes and to see the steady state. And the important thing was a relaxation to the steady state. So that was all, if you like, on a finite state space, this ring with L sides. Today I want to go and take what we call the continuum limit to make it a continuous space. So that's what we're going to do today. And so lecture 2. And then, as we'll see, it becomes a diffusive process. So I'm going to start off by taking the continuous space limit of the random walk. So remember, our random walker, in some small time interval dt, he went to the right with probability p dt and to the left with q dt. And it was by 1 unit. Now I want to introduce a lattice spacing to say that this distance is actually a. And then we're going to take the limit a goes to 0. So if I introduce a lattice spacing a, then also I'll have a spatial coordinate, so which will become x, which is a times j, the number of sites. That will give me the distance. Now also I want to sort of rederive the forward master equation, taking a little step backwards and thinking about how we're discretizing time or thinking about the time. So the idea is for the forward master equation, really what I'm thinking about is a time interval 0 to t, and then I'm thinking about what happens in the next dt. So the important thing is this time interval here. Okay, you'll see what I mean in a moment. So then we say the probability of being at x here will depend on where I was here at time t. Okay? So p of x at t plus dt. So here, if I was at x minus a, then I go to x with probability p dt. So I get p dt, then the probability of x minus a at time t. And similarly, I could have come from one site to the right and gone there with probability q dt. Or I could have just been at x and then nothing happened. And so nothing happens with probability 1 minus these two probabilities. So 1 minus p plus q dt, p of xt. Okay? So then let's first take the continuous time limit. So what I would do is this term here, you see is p of xt. If I take this across here, I get p of xt plus dt minus p xt. And then I'll divide by dt. And this, of course, as dt goes to 0, gives me the time derivative. And that's nice because you see this term I've taken here, the rest of them have dt's, so the dt's just cancel. So as dt goes to 0, this goes to dp xt, make it a partial derivative by dt, equal to, then I've got all this stuff, p x minus a t plus q px plus a t minus p plus q pxt. So that's actually what we just wrote down last time. It's actually quite intuitive. The reason why I've taken a bit more time to derive it is because we're going to, in a little while, we'll meet something called the backwards equation, where I do something slightly different. So that's sort of investment for the future. But so anyway, now we've got our forward master equation, and we have our A in there, lattice spacing. And I want to take A goes to 0, so I just expand in a Taylor series. So now I want to expand. And what I'm going to use is P of X. Okay, so I write the plus or minus. So if it's, let's just do it plus to start with. P of X plus A. For Taylor expansion, it will be P of X plus A P dashed of X, where the dash is simply the derivative, d by dx, plus A squared over 2 P double dash X. And similarly, if I have P minus X there, then the only difference is this term will be minus A P dash of X. This term will be the same. That's what I mean by the plus or minus. Okay, so hopefully you can read that. So the idea is and then I'm just going to keep terms. Okay, so it's plus order A cubed. And as we'll see, I just need terms up to second order. So let me just put this in here and see what I get. So what I'll get is dp by dt. So these terms with no A, they cancel with this guy here. So I'm going to have a P plus a Q, and that will cancel. So the first term are the terms with A, and so I'm going to get a plus P dash from here, no, beg your pardon, from here, and a minus P dash from there. So actually what I get is minus A, P minus Q, P dashed, and plus A squared over 2, P plus Q, P double dash. And just to remind you that the dash is equal to d by dx. I'm just using the usual shorthand. And then, of course, I should just note that the next terms are order A cubed. So what I want to do now is to take the limit A goes to 0. So your first thought is that, when A goes to 0, this is going to be the largest term. And so your first thought would be, yeah, I can just ignore this term. But let's see what happens if you do that, because actually it's not the right thing to do. But let's see what happens. So if I let A goes to 0, this will be you would think is the dominant term. And then, okay, I've got an A here that I want to get rid of. So the game is I should rescale time. So if I rescale time so that if you like, the new time is A times the old time. So if you like, I'm shrinking time. Then I will, here, the d by dt will give me a factor of A, so I can cancel that A, and everything's looking good. And I end up with dp by dt will be minus v p dashed, where v is equal to p minus q, which you would expect to be the drift. Let me just write this out as dp by dx. Actually, I was intending to number equations again, so again, I forgot. So let's call this equation number 1, and this equation number 2. Now, the problem with this is that this is a first-order differential equation. So that's nice, but the solution's actually sort of trivial. I'm saying that A is small, and so I rescaled time, so I had an A here. I then canceled, so this was left with something finite, and this would be A. And so when I say when A goes to 0, I anticipate, that term will disappear. As we see, this is not the right argument, but that would, naively, that's what you would do, right? Okay, the problem is that this equation is first order. It actually has a very simple solution. The solution of, if p is a function of x and t, it's just some function that's actually of one variable, x minus vt. So you can check any function f of x minus vt. If I put it in here, it solves this equation. And what that actually means, it's what I call a ballistic solution. So this is actually just a translation. So all that happens with this solution is that the initial condition is just translated in, well, as time goes on, it's just translated in space. So it just, the initial distribution just moves forward with velocity v, and nothing happens. So it's a deterministic or ballistic solution. So what happens is, if I draw the probability distribution, if I start with some sharp distribution, then as t goes on, then all that happens is that the distribution moves a distance vt, and it remains a sharp distribution. So in fact, I'm not capturing any stochasticity in the dynamics. I'm just getting deterministic solution. And that's not what I want. So on physical grounds, I want to keep this term here. So then, right, so that would be fine. If this term wasn't here, then that would all be fine, because this would be the leading order term in a squared. But because generally I have this term here, I have to be a little bit careful. So I have to instead define an a goes to 0 limit where p minus q also goes to 0, and that's the gain. So there's a little subtle point. I have to have a special limit where p minus q, the drift velocity also goes to 0 with a. So let me do that. So the idea was, I need the order a squared term, which will be, as we'll see, is the diffusive term. So I want to now rescale time so that the new time is now a squared times the old time. So what this means is that d by dt becomes a squared d by the new time. And I'll drop the label new time. Yeah, do you have a question? Yes. A. Yes, exactly. That's the idea. Yes. To get a good limit, you have to assume that. Yes, that's right. So the p minus q is the net velocity. And we find, so to take this continuum limit, that has to go to 0 as well as the lattice spacing go to 0. Okay, so let's do it. So now I'll drop the abbreviation new time. So basically, I've got a factor a squared. So when I divide through by a, and a goes to 0, I end up with dp by dt will be minus v p dash. So let me write it out, dp by dx, plus what I'll call d d squared p by dx squared. So I can read off that v is now the limit as a goes to 0 of p minus q over a. So I need this. So basically, as you were saying, I need p minus q to be of order a. And d is, in fact, just p plus q over 2. And so this is, of course, something you should recognize. And it's, well, you should recognize if I didn't have this term, it would be the diffusion equation. So all this is diffusion, and this term is usually called advection term. It means that there's a drift, or with the velocity, the advection term. Okay, so that's what we wanted to do. So just to summarize, we started with the lattice random walk, and we've had to be a little bit careful with the limits, but we end up with diffusion with advection, and the advection corresponds to the fact that the random walk was biased. Okay, so then probably some of you will have studied diffusion equation, and the solution, yeah. Yes. Yes. Say that again. Well, this is to get this equation. That's what you have to. Okay, that is the limit. So your lattice spacing is going to 0, and also the difference. So the bias also has to go to 0 as a. If you don't have that, then this term dominates, and you end up with some deterministic thing where the drift simply dominates, and the only thing you see is the initial condition being translated. No. Yeah. So all I'm saying is to take a limit a goes to 0, this is what we need this. Or else the first term will dominate. Don't worry about it. Most physicists, we would simply expand and just set a goes to 1 at the end, and then it kind of all works out. But you have to be careful. Yeah. Yes, P and Q are rates. So P and Q over here, the rate of going to right and left. So the difference is the net rate at which it moves. No, this is, okay, it's not a big deal. Let's not get hung up about this. We need that the difference in these rates should go to 0 with a, and then we have a nice limit. P and Q are rates here. Okay, look, this is not, so let's not get hung up on this point. Let's assume we've taken our continuum limit. This is what we end up with. So all I've tried to tell you is what the conditions are on A to make this actually a rigorous limit. But usually as physicists, you would just write down this equation as a continuum approximation. Okay? So the solution of 3 is, of course, it's a Gaussian. So if I have initial conditions, so IC is initial condition, and that P of x at time 0, let's say we start from a sharp distribution, so it's a delta function, x minus at x naught. So it's sharply peaked to x naught. Then I know what happens. The solution of this is P x t will be, the only thing I have to remember are where the 4s go. So it's a 4 pi d t square root exponential minus then x minus vt minus x naught squared over 4 dt. Right? So that's the Gaussian distribution. I leave it as an exercise. You can check that this satisfies this. You'll find it does. And this, okay, and this has the initial condition. So when t goes to 0, this becomes this delta function. And this is known, usually we denote it g of x t given x naught. Okay, sorry, my notation here is, sorry, x naught t. And this is known as the initial value green function, or some of you may know it as the propagator. In sort of field theory language, they call this a propagator. Doesn't matter. It's just a green function. It's a Gaussian. Yes? Well, yeah, it is dimensionally correct. Yeah. Okay, so the dimensions here, so velocity, dimensions of velocity are space over time, and dimensions of the diffusion constant are space squared over time. Okay. Okay, so you're worried. Well, not really. Okay, so here, okay, so, yeah, no, I understand. I'm just trying to relate it to, so it's sort of consistent. So d should be space squared over time. Okay, I see what you're saying. You're worried. Yeah. Okay, so I'm ending up with my p and q having dimensions x squared over t. I'm sorry? Yeah, but I rescaled, that's right, because I rescaled everything with a squared. So that's why. So that's why it's come out of, yeah, I take your point, but it does work out. Phew. Thank you. Okay, so let's now concentrate on diffusion equation. So this is the green function, and you can check it's the solution. So the nice thing about the green function is, of course, that for arbitrary initial condition, so say I have that my probability at time 0 is some arbitrary function. Well, it should be positive, of course, it's a probability. And it should be normalized. But whatever, let's say it's f of x, then at time t, all I do is integrate up using the green function. So I integrate over all, let me say, x primed. Then I have x primed, and I have g of x given x primed in time t. And that will be my solution. So the green function allows me to compute that for any initial condition. So that's why it's a nice thing. Okay, so what we see, anyway, with this is starting from a sharply peaked distribution, what happens as time goes on, it translates the center moves a distance vt, but it gets fatter this time. And that's what we want. So the probability distribution spreads out, and the width goes, we would say, measure of the width is 2 dt square root. So the extent of the distribution increases as t to the half. And this is where we see the dynamic exponent. So the time for it to spread out a distance L, the time takes is L squared. And that's where we get the dynamic exponent, Z equals 2. Now, the thing is, if we're on an infinite system, there is no stationary state. So we start with this sharp peak of probability, let's say at x naught. And it just spreads out, and if you're on an infinite system, it keeps spreading. There's no stationary state. On the other hand, if we do it, let's not do the details, but let's say we're in a box, so a finite system. Then initially, it looks like this, but then after a time, we said the width of this grows as t to the half. So if our box is size L, after a time L squared, then it starts to fill the box. And eventually, it will just be a flat distribution in the box. And we end up with an equilibrium distribution where detailed balance holds and there's no currents. So we end up with an equilibrium stationary state. So let me just draw that. So in a finite system, okay, I need to go up here. So in a finite system, let's say it's a box of size L, and let's say the boundaries are reflecting. So if we start with here, then after a time greater than L squared, the distribution will be basically flat, and it will be an equilibrium distribution, by which I mean there's no current flowing, and detailed balance holds. So the reason I stress this is that diffusion is a fundamental dynamical process, but by itself, we don't get an interesting stationary state. There either isn't a stationary state, or in a finite system, it goes to an equilibrium state. Right, so let's move on. What I want to do now, so just to check, have you all met diffusion and studied the little bit diffusion equation before? Okay, actually not too many nods. So it's as well that I did it then, okay. So let's explore a little bit more now, properties of diffusion. Okay, so what I want to do now is to consider my diffusive particle, which obeys this diffusion equation, and I want to consider what we'll call a trap, and I'll put it at the origin. So the idea is this particle diffuses around, and when it hits the trap, it gets stuck, and it's over. So I want to ask the question, how long does it take to hit the trap? And what's the probability that it survives? And it hasn't hit the trap yet. So, but to do that, I want to introduce a backward master equation. So this is why I did the forward one in more detail at the beginning, because the idea of the backward one is that time now, we want to look at time t plus dt, and the idea is that we put the dt in the first time interval, what happens right at the beginning, and then from there to there is duration t. Right, so I want to say what's happening at time t plus dt, and I work it out from averaging over what happens in the first dt. So if you compare with back here, it was at the last dt that I did here. So let's do this. So again, p of x at time t plus dt. And now I need to focus on the initial condition, given x naught. Well, in the first dt, the particle could have moved to the right, and then x naught for the rest of the time would become x naught plus 1. So p dt, I get p of x t x naught plus 1. And similarly, if in the first time interval it moved to the left, sorry, it's the initial position. Yes, okay, at time 0, we're at x naught. And then here, I want to be at x. I want the probability of going from x naught to x in this time interval t plus dt. I see what happens in the first dt. For the first dt, either I go to the right or go to the left, or nothing happens. So that's if I go to the right, if I go to the left. If nothing happens, then nothing happens with probability 1 minus p plus q dt. Okay. So I beg your pardon. With the lattice spacing a, I should have put x naught plus a here, and x naught minus a there. Right? So now I do the same thing I did before. I expand, first of all, in time. That's easy. I just take this term here, divide by dt. I get a first order derivative. And now expanding in a, I'm expanding in this variable x naught. That's the important thing. So I get my space derivatives are in the initial position, x naught. So I'll leave the details to you. So this can be little exercise. And what I'll get is dp by dt. And this time, I will get, it's the same, okay, and again, I will be in this limit here. So remember, v is this, but this time I get a plus v. And now it's dp by dx naught. And then again, plus d squared p by dx naught squared. Okay, so sorry, it's a bit squashed at the bottom, but that's my backward master equation, or sometimes it's called backward Kolmogorov equation, or sometimes backward Fokker-Planck equation. These are all the same thing for our purposes. So I was meant to be labeling equations again. This is an important equation, so I'll give it a number. Call that number 4. And this is number 5. Okay, so you're happy with that? So this is a backward master equation. And it basically, the spatial coordinate that we're working with is the initial position. And the difference is I get a plus v here rather than a minus v. Okay. So let me now return to the problem of the trap. So let me introduce a trap now at x equals 0. So the way I put this, I want the same equation, and the trap now fixes the boundary conditions. Also, let me take x naught greater than 0, just to fix things. So basically, because when it hits the trap, it gets absorbed, the particle, then x will always be greater than 0, because this trap is at x equals 0. And so my boundary conditions, so BC is boundary conditions. So when I reach position 0, so when x equals 0, then the particle gets absorbed by the trap. So if you like, the probability of it being there and being alive is 0. It just gets absorbed, so it's out of the game. So the probability of it surviving and being there is just 0. And my initial condition, if I try to start it at the initial position 0, if I try and start it at the trap, it just gets absorbed straight away. So the probability of it being alive is just 0. So these become my boundary conditions. So basically now P is the probability P of xt x naught, the probability that particle started at x naught and is still alive at time t and is at position x. Yeah. Well, the probability that it's alive. This is a joint probability that it's alive. And being alive. Yeah. So the problem is it can go to 0, that's fine, but then it's dead. Yeah, so the probability of being alive and at 0 is 0. That's why it's a trap. It's like the fly trap in the canteen. You know, it kills the fly. So the particle here, when it hits the trap, it's dead. So maybe I should write this. So NB, so P x t given x naught is prob that particle it's a joint probability really that it's alive and at x at time t, given it started at x naught at t equals 0. Hopefully that's clear. Is that clear now? So I'll consider the case V equals 0, so no drift in this equation. So I'll have dp by dt. Okay, so I'm just writing out equation 5 there, but with no v term. So what I'll call the total survival probability is, okay, it doesn't matter where it is. I just want to know the probability that it's still alive at time t. So I integrate over all possible positions from 0 to infinity. I integrate over all places it could be, and that gives me the total probability that it's alive. So I'll call this the survival probability. I'll call it Q. And it now becomes, I integrate out x, so it becomes Q survival probability at time t, given that it started at x naught. So the integral over x from 0 to infinity of p x t x naught. So the nice thing is, and now you'll see why I use the backward equation, I can, because this variable here is x naught squared, I can just integrate over x. And so the p just becomes q. So the q obeys exactly the same equation, this backward equation. So that's the magic with the backward equation. So this equation here simply becomes dq by dt when I integrate out x. equals d squared q by the x naught squared. Okay, so let's make that equation number 6. And my boundary conditions now become, so here these were the boundary conditions. So when I think about the total survival probability, well, at t equals 0, then as long as x naught is not 0, at t equals 0, it will have survived, right? It hasn't had a chance to die yet. So the survival probability should be 1. So the initial condition is q of 0, x naught equals 1. That's for x naught does not equal 0. And whenever, if it tried to start at x naught equals 0, then, okay, it doesn't survive. At the moment that it's at x, the moment the initial position is 0, it's trapped. So that probability is 0. So this is the initial that's the initial condition. This is the boundary condition. So what I want to do now is to solve this diffusion equation subject to these boundary conditions. Now, there's many ways of doing this, so I'm not going to give you them all. You may have heard of things like method of images is one way to do it. I'm not going to do it that way. I'm going to do it a more systematic way that we'll then use in the second half of the lecture. So I'm going to solve this by Laplace transform. So remember, okay, Laplace transform you've probably all seen. You may not have actually used in anger. The idea is you transform your equation, and it becomes easy. You solve it, and the hard part is then transforming back. That's always the hard part. But I'll say a few words about that. So let's solve this equation. So the LT is Laplace transform, and it's defined, I'll write it as Q tilde. So my variable t becomes an S. So I integrate out from 0 to infinity dt, and I put an e to the minus st there, and it's q of t. Okay, so that's the definition. So when I want to Laplace transform this equation. Only tricky bit is transforming this side here. Let me just think a little bit about that. So if I try to make the transform, I have integral from 0 to infinity dt, e to the minus st. Then I've got a dq by dt. And that I integrate by parts. So remember, integrate by parts, you integrate 1. So actually, let's put in the q t dependence, q t given x naught, from t equals 0 to infinity. And then I differentiate the other part with a minus, so I end up with a plus s. And in fact, I'll just then get the Laplace transform. So this bit becomes, okay, the t goes to infinity, limit is 0, or value is 0 because of this. But I get something from when I put t equals 0, I get a q0 x naught, which is 1. So in fact, this is minus 1 plus s, and this is in fact q tilde. So when I Laplace transform 6, I get d. Okay, from this term here, I get d squared by dx naught squared of q. So q tilde rather. Won't write out the arguments. Then this one here will become minus s q tilde, and I'll get is equal to minus 1 here. So this equation, hopefully that's clear, this is what I need to solve. And this is quite easy to solve because it's effectively The differential equation is in x naught, so it's just a second order differential equation. So you should be well trained in solving these. And it's got an inhomogeneous term, but we can easily write down the general solution to this equation. It's going to be q tilde. So first of all, I write down solution to the homogeneous equation when this is 0, and that is, so it's some constant a, e to the minus alpha, let me write it alpha naught, x naught, plus b e to the plus alpha naught x naught. So that's the solution to the homogeneous equation. And then I need to find a particular solution when the right-hand side is minus 1. That's easy. I can just choose q tilde is 1 over s. And that's a particular solution. Right, so 1 over s is a constant, so that term would be 0. So it works. So that's a particular solution. Plus 1 over s. And this is the particular solution. Sorry, it's a little bit messy. So it's these two terms plus 1 over s. Then I need to just fit the boundary conditions. So what I say straight away is that this term, oh right, so an alpha naught here is the square root of s over d to the power half. So I call that alpha naught. Okay, so that was just solving this equation. Now I know that q is a probability. The maximum value you can take is 1. So I need to fit these constants a and b, and straight away I see that b has got to be 0, because otherwise this would diverge as x naught becomes big, and it can't do it. It's got to be less than 1, so I can't have that term there. So b naught's got to be 0. The reason for that is q tilde should be finite as x naught goes to infinity. And this means b equals 0. Then we have the condition, what I call the boundary condition, that q of s when x naught equals 0 equals 0. So I'm left, when I put x naught equals 0, the a must cancel with that. So and so the job is done. It actually wasn't too difficult. And the solution to this with the boundary conditions is, if I put it all together, I get q tilde sx naught equals 1. So let me write out the alpha naught. So let me label that, because I'll refer to it later. I'll put it in a little box so that we can see it. Okay, so as I told you, that was the easy bit, is solving for the transform. Now the hard bit is inverting this. So there's a number of ways of inverting Laplace transforms. And I have to confess, the easiest is to look it up in a book. And for this one, I'll say, hopefully, next lecture, if I have time, I'll explain how you can do it if you don't have your book with you. But for the moment, it's easiest just to say that this, it turns out, it's a standard Laplace transform that you can look up in a table. And it's a Laplace transform of the error function. So I'm out of... Okay. Let me... If I can just use this board. Sorry to jump around. I just need one more board to finish off this calculation. So if I invert equation 7, you can do this by looking up our table. What I find is Q, the survival probability at time t, starting from x naught, is in fact the error function of x naught over 2 square root dt. So an error function is sort of an incomplete Gaussian integral. So the definition of Earth is 2 over pi to the half, that's just a normalization, integral from 0 to z, e to the minus u squared du. So you see when z goes to infinity, you can do the Gaussian integral, and you get 1. And when z equals 0, you get 0, because there's no integral. And in fact, you can expand for z small. You can just expand this and integrate term by term. So this error function for z small, okay, I expand the exponential, integrate term by term. So I get 1, integrate, I get z. So I get 2 over pi to the half z, and then the next term will be minus the third z cubed, and so on. So what I see is, so that's my solution. And if I look at large time, which is usually what I'm interested in, then the survival probability after a large time, this argument will be small, so I can just use this as an approximation. So at large time, my survival probability is approximately x naught over root pi dt. So what do I learn from that? Well, the survival probability decreases to 0 when t goes to infinity. So it's like the fly will eventually get caught in the trap, after a long time. So the interesting thing, that's fine, but now let's think about the mean time for it to get absorbed. How long does it take, on average, for it to be absorbed? So we can get that by noting that the rate of absorption let me call this capital Q. So the rate of absorption is actually, now you need to think about this a little bit, it's minus the derivative of the survival probability. So if you think about it, if the survival probability is decreasing, that means that at time t, that means there's some chance the rate at which it decreases is the rate at which the particle will be absorbed at time t. Because when it gets absorbed, you lose survival probability. You just need to think about that. It's actually a simple thing. So it's minus dq by dt, so it's easy to take derivative. And I'm going to get 1 over 2 x naught over root pi d. So let me emphasize it's 1 over t to the 3 over 2. So then, the mean time to absorption. Now this is often called the mean first passage time. So I might use that abbreviation later. So basically, it's the average of the first time that the particle touches the origin, because whenever it touches it, it gets absorbed. That's why it's called mean first passage time. So I would get that, so let's call it t, by integrating the rate at which it's absorbed, so that's basically will give me the probability that it's absorbed in time t to d plus dt, times t. So I end up with minus t dq by dt. Okay, integral with respect to t from 0 to infinity. So all I've got to do is calculate the integral. So here, dq by dt is here. And I've got a t there. So it's going to go like some constant, then times minus integral from 0 to infinity, 1 over t to the half. So who can do that integral? But the definite integral. Okay, so it's, you said, right, you want to integrate, you get t to the half, but the limits are 0 to infinity. Okay, it's a kind of trick question. This integral is not defined, it diverges. So this is the point. So we didn't do anything wrong, just that's the answer. The mean time for it to reach the origin is infinity. So it's a rather curious situation. We've shown that with sufficiently large time, the particle will be absorbed with probability 1. It will be absorbed for sure. But if we ask how long do we need to wait for it, on average, for it to be absorbed, infinity. Sounds a bit strange. So the reason is, so the particle starts at x naught. Okay, if it goes towards the origin and gets absorbed, all well and good. But it could go the wrong way. And then it's got an infinite space out there, and it can keep going. So sometimes it just keeps going. And for those trajectories where it goes in the wrong direction a long way, it takes a very, very long time for it to come back. And those trajectories mean that the average time for it to be absorbed is infinity. So this is often called the persistence of bad luck. I don't know, maybe, I don't know if gambling's acceptable, but right, if you're gambling, it might go, you know, your winnings might go up and down. So the persistence of bad luck is that if you start a little bit down, you know, if you're equally going backward and forward, the time to you to recover your loss will be infinity. So it's the gambler's ruin, or the persistence of bad luck. Okay, so that's the first half of the lecture. Yeah, okay, I'm running a little bit short of time. So let me just clean the boards. We'll have a little 2-minute break there while I clean all the boards. Okay, so I should have just, if you're taking notes, here this was the fact that this goes to infinity, it's called persistence, or the gambler's ruin. Okay, so the two things here was that for large t, this goes to 0. So the survival probability goes to 0, but the mean time to absorption goes to infinity. They were the two important results there. Okay, so, right, let's continue with diffusive processes. I want to talk about a slightly different situation now. So if I'm at home, back in Edinburgh, in my house, there's a place where the keys should be by the door. So when I come in the door, I should hang up the keys, and then I know where they are. But usually I get up in the morning, I go to where the keys should be on the hook, and they're not there. So what should I do? And of course, you start to look for the keys. So then there's this hook, and there's a little table, so I look on the table, and then I don't find the keys, and I wander over to the kitchen table and try and look there, and then I wander maybe to the bedroom, and at some point I realize, what am I doing here? I'm looking for my keys, and I'm not finding them. Where should the keys be? And so what a natural thing to do is then to go back to the place that the key should be, by the hook by the door, and to start to look again. Okay, and so I'm getting a bit old. I kind of forget that I've already started looking, so then it continues until I find the keys. And the question is that, so what I do is I go back to where the keys should be, or where I think they should be, and I start again. So I reset my looking for the keys. And the question is, right, is that a good strategy for finding my keys? And in fact, it turns out it's not so bad, but I'll try and demonstrate this to you. So one thing I should say, so now let's think in terms of the diffusive particle. If my kind of looking around, if this is modeled by diffusion, so if I did not reset, and so let's say the keys were somewhere and I was searching for them, then what we saw in the first half of the lecture is that the time for me just diffusing to locate the target is in fact, well, in one dimension, it's infinite. Because if I go off in the wrong direction, so let's say I wander out of my back door and I wander out into the garden, I'm not gonna find my keys. And so by resetting, by going back to the beginning, can I improve upon this infinite time to find my keys? So that's the scenario. So what I'm going to consider now is to see, diffusion with stochastic resetting. So the motivations, so I've just described to you roughly what I'm going to do, but the motivations are, first of all, this search problems, maybe not in all seriousness optimizing the time for me to find my keys in the morning, but there are various search problems, like animals looking for food. They have periods where they kind of forage around locally. You think of that as diffusion, and then if things are not good, they will all pack up and go off on a big migration and then go somewhere else to search. So they have these long-range moves and local search. So that's one example, animals foraging. And also you can have, for example, proteins. They want to come and bind on RNA so they can do the translation of RNA. We're jumping to biology now. It's a very long molecule, so how do they find the right place to land and to bind? And they will bind and then jiggle around, and if it's not happening, they will detach and then go and bind elsewhere. So you get this local diffusion and then some long-range moves. So animals foraging, proteins searching for binding site. And also, for example, internet search. If you're searching for something on internet, there's some local moves, and every so often it's a good idea to go somewhere completely different, a different part of the internet to search there. So internet search. But the second motivation is, I stressed in the first half of the lecture that diffusion, if we're on an infinite system, we don't get a stationary state. It just relaxes. And if we're on a finite system, we get equilibrium state. And by resetting, by having diffusion and constantly resetting it, we're actually going to generate a non-equilibrium stationary state. So I guess this is my real motivation for being interested in this problem. So resetting of diffusion, for example, leads to a non-equilibrium stationary state. And that's because you never allow the system to relax. You're always putting it back to the initial condition. So the stationary state is, in fact, a snap, if you like. It's a sampling of the system when it's relaxing. Okay, so the model, I'm going to have my diffusive particle again. So let's write it now directly as a diffusive particle. So in a continuous space, so it's going to the right or left with rates d dt. And then it will, let's say it goes back to the reset position, and this is in time dt with a probability r dt. So r is the resetting rate. Now, to make life a little bit simpler, this is the position it resets to. In principle, I can have a starting position and a reset position that are different, but I'll take them to be the same. I say it starts at here, diffuses, and then I put it back to the same position. In principle, they could be different, but let's assume for the moment that the initial position is the reset position. Okay, so let's just write down the forward master equation. Remember this, we can usually write down forward and master equation without having to think too hard. It's the backward one we have to be a little bit careful with. So, forward master equation. Okay, so I'm going to have dp by dt, and it's going to be x. So here, sorry, let's also say no absorbing traps for the moment. First of all, I just want to consider diffusion with resetting, no target or trap. So x naught, remember here, it's kind of, x naught is the starting position and the reset position. Okay, this makes life simpler if I have one, otherwise I'd have to have two things it depended on. So I'm going to have diffusion. This is the forwards equation, so the derivative with respect to x. Then I have, right, I'm resetting from anywhere with a rate r. So I'm going to get a loss term minus r p of x t x naught, t there. And then when I reset, I go back to the origin. So I'm going to have if x is x naught, then I have a gain term. So it's r, and then it's actually, I'm resetting from all positions. So I'm going to integrate over x from minus infinity to infinity, p of x t x naught. Okay, so this is because I'm resetting to x naught from anywhere. But then, of course, because in this case, the probability is conserved, the integral of the probability is 1. So this term is just 1. So I just get an r. So that is all just 1. So my forward equation is a diffusion equation. And it's just got, if you like, these two new terms, a loss from all positions x. So it's a little bit unclear. It's x of t given x naught, and a gain term at x naught. So first of all, let me try, and so as I said, there will be a stationary state. Let me try and compute it. So I want to calculate the stationary state. Stationary state, the dp by dt is 0. So I'm going to have this term d squared p, okay, I won't write out the arguments now, just say by dx squared, minus r p of x equals minus r delta x minus x naught. So this, again, if I look at the left-hand side, it's a simple second-order differential equation. I should be able to solve this. My only worry, we've got a delta function here, so that might scare me a little bit, but actually there's nothing to worry about. This delta function, if I'm away from the delta function, you see I just have 0. So it's just a homogeneous equation. So let's look at the homogeneous equation first and then sort out what happens at the delta function. So the solution of homogeneous equation would be p equals some constant a, e to the minus alpha naught x plus b, alpha naught plus b. So this time, I've got a slight clash of notation. I used alpha naught in the first half of the lecture when it was something slightly different. So, but here, alpha naught is the square root of r over d. So the solution to the homogeneous equation is when I put this equal to 0, then you see these are solutions. So if I'm to, let's say x is less than x naught, that includes, let's say x is greater than x naught, that includes x goes to infinity. So I want to avoid this term here, because that would diverge. So if x is greater than x naught, let me write the solution p equals 0. Let me write the solution p, and let me just fiddle around a little bit with this constant. So let me call it a tilde, and I'll write this as e to the minus alpha naught x minus x naught. So I've actually put in an e to the alpha naught x naught, which is a constant. That's why this a tilde is a different constant from that one. I've just been a little bit slick there, just to make life easier. And similarly, if x is less than x naught, then, okay, that includes x goes to minus infinity. So then I want to avoid this term, so a should be 0. And I can write p as b tilde e to the plus alpha naught x minus x naught. That's right, because, x then going to minus infinity, I'm okay. And so all I have to do is then determine the constants a and b. And the way to do this, we've got a delta function here. I'm sorry? Because then we had a boundary. We did. We had to worry about x goes to infinity, but we had a boundary. Okay, here there's no boundary. So we have to worry about what happens at delta function. So actually what happens is that our function, you see we've got two different forms. The rule is that we expect the function to be continuous, but the delta function will actually introduce a discontinuity in the derivative. So first of all, we can fix one of the constants by just demanding that p is continuous at x equals x naught. So continuity of p at x equals x naught simply implies, the way I've written it, that's nice. When I put x equals x naught, I get 0 here, so I just have a tilde equals b tilde. And then I can either fix a tilde by, from this equation, the delta function actually implies a discontinuity in the derivative. But it so happens that there's an easier way to do things. I could go that way and work out the discontinuity, but actually, here it's easier. I just say that the probability needs to be normalized, and that fixes my constant a, and it does the same thing. So it's easier here just to demand normalization of probability. So if I normalize, so integral over x of px equal to 1, then I get that my stationary distribution, let's call it p star, of x, given my resetting position x naught, is actually alpha naught over 2. And again, I'll leave that as an exercise for you to do the normalization. That's an alpha naught. So if I draw my P, and this is x, and let's say x naught is here, it looks something like this. So it's an exponential decay on both sides, and it's a well-defined stationary state. So it's, of course, peaked at x naught, because that's where I reset to. Now, the interesting thing is that if I look at the flow of probability, I actually see the arrows here are meant to indicate the flow of probability. So probability, because it's diffusion, probability will flow down the gradient, so it will flow out the way. But then it gets reset, so the probability flows back into there. So if you like, it's a non-equilibrium state with the probability circulating around because of the resetting. So this is a useful sort of paradigm to generate simple non-equilibrium states and to study them. So I've got a little bit of time left. I don't know how I'll finish this, but I will try. So that's the stationary state. And these arrows are meant to indicate the current of probability. So we get a circulation of probability. Okay, so now we're going to consider an absorbing target, and let's make it at x equals 0 at the origin. And what I want to do now is to determine the survival probability and, more importantly, the mean time to absorption. So what I'm going to have to do here is to derive, first of all, the backward equation. Remember, this is the best approach to calculate survival probabilities, is to use the backward equation. So we have to derive it for the resetting. And the backward equation, okay, I guess it's one of these things, if you're smart enough, you can just write it down. Most of us have to think a little bit. So let's just derive it slowly and make sure we get the right answer. The complication is, remember, in the backward equation, the initial position is the variable. Right, so now I'm going to have to allow the initial position to vary, but I want to keep the resetting position fixed. So they're two different things now. In the first half, I made them the same. Now I have to let the initial position be a variable and have a separate resetting position, which I'll call xr. So z is now the variable initial position, and let's write it at xr is the resetting position. Okay, so what's happening is so this is my position z, and I have my usual diffusion, which I'll indicate by, in some small time interval, going to the left or right with the rates d. And I have also resetting to position xr with the probability r dt, so rate r. So my backward equation, I'm going to have P of x t plus dt given, so z is now the initial position. So what I could do is to go to the right or to the left. So I have d dt p x t z plus a plus d dt p x t z minus a. Now also, in the first, remember, I'm averaging on what can happen in the first interval dt. I could reset. So I could then start from the resetting position xr. So with probability r dt, I go to xr, and then I have probability of going from xr at time 0 to x at time t. And or else nothing can happen. So with probability 1 minus 2 d dt minus r dt, then I just go from z. I need to go from z to x in times t. So then I do the usual stuff. I take that term across here, divide by dt to get a time derivative, then expand these guys to get the spatial derivatives and do the rescaling and all. And what I end up with is dp by dt, now it's xtz equals d squared by dz squared. So that's the usual diffusion bit. Then I've got a plus r, p xt and x r here, and a minus r p t, say x t z. So it looks a little bit different from the forward equation, where, okay, this term is going to be different. That had a delta function there. It looks a bit different now. It's, we reset to this initial position here. So it's just as well that we took our time to derive it. Okay, so now we want to play the same game. That's the backwards equation. We've got now a trap that we're going to put, let's put it at the origin. And let's say that our resetting position is bigger than 0, and our initial position is bigger than 0, just to make that simple. So we define our survival probability. Again, let's call it Q, T given Z. So I integrate over X of P X T Z. And that's the magic, that you can simply integrate each of these terms, and it's that you get the same equation for Q. So we've got dq by dt equals d squared by dz squared q t z minus r q t z plus r q t given x r. So let's just follow the same path that we did before. Let's try and solve this with Laplace transform. So again, we define our Laplace transform. Q tilde is by definition integral from 0 to infinity dt e to the minus st q of t. Well, okay, I've suppressed the z dependence, but okay, I'm just defining a Laplace transform. And we play the same game. And okay, if we do that, we end up with d q tilde double dash. The dash now is derivative with respect to z. And again, when we do this, we're going to get we generate an sq tilde term. So we end up with minus r plus s q tilde. And then, okay, from here, remember, we get a 1, or a minus 1. And now this term, let's take across to that side. Okay, so really, I'll leave it to you to fill in the gaps there. It's just a simple generalization of what we did in the first half of the lecture. So, thing is, yeah. So these Q's, so the dash now is d by dz. So actually, this is a function of z, and this is a function of z. So this term here doesn't depend on z. I mean, it depends on s, but this differential equation is with respect to z. So basically, I can treat this term as a constant and then just solve this equation. And we use a similar technique before. So this is just, as we did before, this is just a second-order differential equation. This is a constant. So the general solution, Q tilde, let me put back in the S dependence to indicate that. It's A e to the minus alpha z plus B e to the plus alpha z plus 1 plus R Q tilde XR over S plus R. And that's the general solution. So remember, so this is the solution of the homogeneous equation. This is a particular solution. Q is a constant, okay, which then that equals that. And alpha this time is R plus S over D to the half. So the boundary conditions remember is Q, the survival probability at a time 0 should be 1. So that means it's bounded. And the survival probability at any time, if the starting position is 0, then the survival probability is 0. So putting those two things in here, we see we have to lose this term because it would lead to an unbounded survival probability. So that implies B equals 0. And this term, then if that's gone, then we need A is simply minus that when Z equals 0. Okay. So we can check, yeah. So that gives us Q tilde, and A, and here we've got Q tilde of S, of XR. So this might seem complicated, but then it's easy. Ooh, okay, I just finish up. Then all we need to do is, we've got Q tilde for general Z. If we just put Z equals XR, then we get a self-consistent equation for Q tilde at XR. So let me just say, I'll let you do that. Fix Q tilde of S XR self-consistently. And our result that we get is 1 minus exponential minus alpha x naught over S plus R exponential minus alpha x naught. Now recall, remember, alpha equals S plus R over D to the half. So that's our result. I'm afraid I didn't keep up with the numbering, so I'll just make this equation star, important one. We'll look at this next time. I'm not going to go through it now. But the important thing to note is that if I take R goes to 0, so I should recover the result from the first half of the lecture, just diffusion with the trap at the origin. And you see that I do. If I take R goes to 0, I lose this term, and alpha becomes alpha naught. And I get that result. So this generalizes the previous result to the case where I have resetting. And what I'll show you next time is that the really nice thing is that having R there reduces the mean time to absorption from infinity to something finite. And in fact, as we'll see, there's an optimal choice for R. You can change this mean absorption time by varying R, and there's a best choice, which we'll discuss next time. Okay, any questions? I'm sorry, the last term? Yeah. So this term here is a loss. From all points, we lose probability with rate R. Then all that probability goes into the resetting point, which in this case I had was x naught. So that's the delta means that all that probability is a plus. So it's a flow of probability into x naught. And it's coming from all the other positions. So it's the integral of this term, this loss term, from all the other positions. So I integrate this from x equals minus infinity to infinity. Then because probability is conserved, the integral of the probability must be 1. So that's just 1, so it just becomes a delta x minus x naught times R. Yeah? So it's saying that we get a, right, so we have a loss of probability from everywhere. We have a gain of probability. The delta means that we only get the gain of probability at position x naught. That's where we're putting all the probability back in. Any other questions? Okay, tea time.